Good. All right. So our next speaker will be Marco Serra, who will be giving a talk titled "On ADS Solutions from Scherk-Schwarz Orbifolds." All right, Marco, please take it away.
So, hi everyone. Let me start this talk thanking the organizers for giving me the opportunity to present here my work, which is based on work that appeared over the summer with my supervisor, Parameswaran. And the title is On the Sitter and Anti-de Sitter Solutions from Scherk-Schwarz Orbifolds. So to begin with, I will indeed notice that the recipe for the Sitter vacua in string theory is rather involved. And in the current paradigm, which is either Haeckel or LBS, we need to engineer a warped Calabi-Orbifold compactification that usually comes with a huge number of massless moduli. And therefore, we need to turn on perturbative and non-perturbative effects to stabilize all these moduli. But once we do so, we usually land in ADS. That's why we need an uplift mechanism to reach the sitter. So left aside all the control issues of this recipe, this is surely a very involved recipe. On the other hand, one can ask, what about classical de Sitter solutions? So these are solutions in the classical corner of the string landscape. Here we only have three-level ingredients like fluxes and curvatures, and a plane to break the strong energy condition. Yet there are the so-called open problems, as these solutions are commonly believed to be all tachyonic, and there's no parametric control. In particular, one cannot obtain parametrically small string coupling, and at the same time, large internal volume once string theory inputs are given. So let me now highlight that so far, localized sources have been used to break the strong energy condition, which is a necessary step for the sitter. At the same time, we also have to break supersymmetry, which again is mandatory for the sitter. And this has been done at the FT level. So it seems that we are neglecting a corner of the landscape, which is the non-supersymmetric corner given by the non-SUSY strings. Therefore, we can ask whether the sitter is hiding in these non-SUSY string constructions. Or in other words, we can ask whether a pure stringy SUSY breaking can serve as violation of the strong energy condition and perhaps could lead to de Sitter solutions. So string theory comes with two classes of non-supersymmetric strings, where the SUSY breaking is described, is realized in a top-down fashion, consistent with the rules of string theory. The first class is SUSY breaking at the string scale. So here we have the 3-10D tachyon free theories. So we have the heterotic SO16, SO16, and then two orientifold theories, Sugimoto USP32 strings and the 0' Bisagnotti string. And here the sec is violated by the presence of 10D dilaton tadpole potentials. Yet here there's no de Sitter solution, as shown by Nogo by Basile and Lanza. However, string theory offers a second possibility, which is breaking supersymmetry spontaneously at the Kaluza-Klein scale. And this is done in the context of type 2 Scherk-Schwarz orbifolds, which indeed realize this breaking spontaneously by compactification. So in this talk, we're going to explore whether this can be an arena to obtain de Sitter solutions. So the plan goes as follows. I will quickly review the Maldacena-Nunez theorem for de Sitter. Therefore, I will present the Scherk-Schwarz mechanism in string theory, and I would then provide you with Nogo theorems for metastable de Sitter solutions once this Scherk-Schwarz orbifold is implemented in string compactifications. So right, I will also, in that part, address 3 points: existence of solutions, stability, perturbative stability, and parametric control. So for the first point, we will see indeed that these solutions are not obstructed, as it happened for the SUSY breaking at the string scale. However, any de Sitter solution will be, at best, unstable. And indeed, we detected a universal tachyon whenever the space-time dimensions is bigger or equal to 4. And then we can still ask whether we can have control on these saddles, and the answer is no. And indeed, again, any putative de Sitter solution has to realize this scaling. So GS has to grow in terms of the internal volume, and the constant is indeed a flux number, which is fixed to be an integer according to the string theory rule. So again, string theory inputs are going against the parametric control, and this is not happening, as we will see, for ADS solutions. So very quickly, for the Maldacena-Nunez de Sitter theorem, as every of you know, in a warped compactification of gravity, the Sitter spacetime is obstructed by means of a strong energy condition. So if you define this effective trace of the stress energy tensor, then the equation of motion will give you this integrated constraint. And under the assumptions that here we have only tree-level in GS, no alpha prime corrections, and non-positive scalar potential, then this t tilde is non-negative, which means by means of this constraint that the Sitter is not realizable. We will see that in our Scherk-Schwarz compactifications, due to the supersymmetry breaking, we are producing a one-loop potential, which is violating the assumptions A, and this potential is such that t tilde is negative. So at least there could be arena where to look for the Sitter solutions. So now let's come to the Scherk-Schwarz mechanism in string theory. The idea is field theoretic. So is indeed giving masses to the fermions by means of antiperiodic boundary conditions. So to explain you the basic realization, we can consider 5D field theory compactified on a circle S1 of radius R. So here usually we would require for periodic boundary conditions, which indeed will give you the standard KK decomposition. But this is not the end of the story, because if the theory has a symmetry T, where Q is the generator, then we can twist this condition, these boundary conditions, which means that we can ask for the periodicity up to the action of T. So here you see now that the KK decomposition is going to be affected, and the KK number is going to be shifted by quantity, which is Q over F. And crucially, this means that also the mass spectrum is going to be affected. So now if you set Q to be the spacetime fermion number F, then T is nothing more than the fermionic parity. We will see now that zero modes of fermions and of fermions only will acquire a mass. So this is breaking supersymmetry, and the SOC breaking scale is set at the mass scale of the zero mode of fermions, which is roughly the KK scale. So here we are indeed realizing a spontaneous breaking, and supersymmetry is recovered in the compactification limits. So the way to implement this Scherk-Schwarz mechanism in string theory is by means of an orbifold procedure. Again, I will give you the realization in the ISES case, which is again an S1 case. So we can consider type 2B compactified on a circle with coordinate y. And we have to mod out this theory by this orbifold G, which is given by a -1 to the F coupled to delta y. So F, again, is the space-time fermion number, while delta y is a free link acting shift, which is acting in the same way in the left and right part of the coordinates as a shift of pi r over 2. So to describe this theory, we have to obtain the orbifolded torus partition functions, which means that we have to compute the trace of this orbifold projector acting on the states of type 2B on this one. So we know what this object is. This is given by this formula here. So let me explain you very quickly how to read off these amplitudes. So we have a first part given by V8 minus S8 square. This is the information coming from the oscillators of the string. I'm using these SO8 characters, which are defined in the following way. So they are, V8 is the GSO contains information coming from the GSO projected NS sector, and same for S8 for what concern the Raman sector. So here I'm telling you nothing more than, for example, V8 square is the usual NS sector, and for example, V8 S bar is going to be the NSR sector, where the gravitino is, and this is going to be the sector where we will about to detect the SOC breaking. And lambda Mn is the usual S1 lattice. So here you will have KK momenta and winding contribution to the left and right internal momenta. So once you compute this amplitude, and perform custom mirror scaling of the radius, you will obtain this answer. So again, let me show you how to read off this amplitude, the spectrum. So you have the first line. The first line is nothing more than the states coming from the action of the orbifold on the type 2B states. And indeed, here you see again V8 and S8 characters. So we will have Jess bosons and Jess fermions. And keep in mind that this sector is coming with uneven winding. However, since the amplitude must be invariant under the modular transformation group, we need to add twisted states. And indeed, we have this second line. And this line now is given by the wrong GSO sector. So here we have these O8 and C8 characters appearing. They are nothing more than the wrong GSO projected NS state and Ramon state. So O8 is nothing more than the complement of V8 and C8, the complement of this S8. And this whole sector comes with outwinding. So now if you explore the bosons, now you're going to see that they come with integer M, whereas all the fermions comes with semi-integer M. So the gravitino is in this sector, which means that now the zero mod is acquiring a mass, which is indeed implementing the Scherk-Schwarz, the Kaluza-Klein state, Kaluza-Klein scale. However, in string theory, there's a price to pay for that. And indeed, now you realize that since we have this presence of the O8 sector, this O8 will start at the lowest level with the NS vacuum, which is not anymore now projected out by the GSO projection. And this vacuum is tachyonic. So now if you figure out the mass formula for taking into account the winding contribution, you're going to see that in the spectrum, there's a scalar, which is tachyonic whenever the radius is smaller than square root of 2 alpha prime. So we can indeed understand that this spectrum is interpolating to type 2B in the compactification limit, where we recover supersymmetry. Whereas in the opposite limit, we eat this tachyon, and indeed we are flowing in a non-SUSY theory, which is tachyonic, and this is 0B. So it's a theory made of only bosons, as we can see that in this limit, all the fermions decoupled. So from the torus, we can also compute the vacuum energy. So we have to integrate the partition function in the fundamental domain. We are interested in the larger limit, where the spectrum is tachyon-free. And in this limit, these are the mass hierarchies. So we see that the KK scale, which is setting the SUSY breaking scale, is the lowest scale, which means that all the massive string states and the massive and the winding modes are extremely heavy. So they will yield exponentially suppressed contribution to the vacuum energy at one loop. And therefore, we understand that the leading order will be set by the KK modes of the massless string state, which are propagating along the S1. So if you work out the integral, you obtain this formula. So this is a runaway potential for the S1 radius. So the power is matching the number of the spacetime dimensions. And the coefficient is set by the massless Fermi minus Bose degrees of freedom. So this is a Casimir-like one loop vacuum energy. But if now you remember that because of the action of the orbifold, all the fermions have been massed up, so we are left with a surplus of massless bosons. Now you realize that this is a negative runaway. So the situation is as follows. So this one-loop vacuum energy effective potential is pushing the radius to the origin, so it's making the S1 collapsing till the point where it's going to hit this tachyonic region where the perturbative control is spoiled. So the idea is whether we can stabilize this runaway within a controlled Metastable de Sitter solution using easy ingredients, so fluxes and curvature. So we want to be in the EFT limit, far away from this tachyonic region. So to do so, we indeed embed this Scherk-Schwarz construction in type 2 unwarped proto-compactifications. So the internal space now is given by a direct product of our Scherk-Schwarz torus, where we implement this SUSY breaking, and Y factor, which is now a curved Euclidean space. So we will use then the ingredients, which are the classical ones, so fluxes, any kind of flux. We also consider D to be equal 3, so we will have H7, F7 as well, and the Y curvature. So these ingredients have to be balanced against this quantum correction, which is indeed our loop, then the Casimir energy, and possibly, of course, in a controlled way. So in the next slides, I'm going to use this notation here. So I will decompose the fluxes in terms of flux components. So whenever you see this upscript here, it means that this flux component will have SQ legs along the Y space and the remaining Q minus SQ legs in the Scherk-Schwarz torus. Also keep in mind that we are working in the EFT limit. So in this limit for very large radii, let's say, all the twisted states from the orbifold are very massive because they come with these non-trivial winding modes, and so they can be safely integrated out from the EFT. So if now you inspect the contribution to the Casimir, from the Casimir to the stress energy tensor, this is what you obtain, and it's very easy to check that this tensor is then traceless. So now if you work out the strong energy condition, then you realize that indeed, if you remove the trace, this is violated whenever the lowest dimensional trace is positive, which happens whenever the B1 loop is negative. And we know that this is holding whenever we have a surplus of massless bosons. So we can indeed break the strong energy condition in the context of a 2B Scherk-Schwarz orbifold, because indeed here we have a surplus of massless bosons, which are generating a negative Casimir energy. So we don't need O-planes to do that. This is done by the one loop vacuum energy. So now the Sitter-no-go. So we want to obtain the Sitter-no-go theorems, and the strategy is to exploit linear combination of some of the 10D equation of motion in the stream frame. And whenever we will able to obtain linear combinations which are indeed given this inequality here, where the right-hand side is non-positive definite, then this is the Sitter-no-go. And in concrete, we're gonna combine the dilaton equation of motion, the lower dimension Einstein trace, and the partial internal Einstein traces. In total, we obtain 4 linear combinations, which are providing us existent conditions for the Sitter. So for example, this is the first one. Here you see that the right-hand side is non-positive definite unless the lower dimensional trace of the Scherk-Schwarz contribution is positive. And indeed, here we recover the previous result. We need, as existent condition, we need a negative Casimir energy. So this is kind of extension of Maldacena-Nunez to a loop in this model. The second linear combination is this one. So here again, you see that the right-hand side will give you a no-go theorem unless the white space is positively curved. So for these solutions, we need to have a positive curved white space. For the third one, the game is the usual one. Here you see that this is the only positive contribution, which means that for any solution, the Ramond-Ramond flux with SQ index must come with a rank Q, which is obeying this inequality. So this again should be present for a de Sitter solution to be possible at all. For the last one, we see indeed that we need to have this H3 flux, which again I stress that this means that H3, the NSNS H3 must have a component which is threading completely the torus, the Scherk-Schwarz torus. And if you work out again now these conditions, you realize that this imply a bound on the spacetime dimensions. So for the Sitter, we need to have a spacetime dimension at most equal to 5. And as we will see momentarily, these very same conditions for the existence of the Sitter are problematic for control. In particular, the presence of an H3 flux which is completely threading the torus is indeed violating parametric control on the Sitter solution. So to discuss stability and control, we use an EFT approach. Particularly, we keep track of the universal moduli, which are given by the lower dimensional dilaton and the two volume of the compactification. So by dimensional reduction, we will obtain the scalar potential, which indeed is given by the tree level plus the V1 loop contribution. And the thing is that in many instances, this universal moduli would correspond to a subset of a consistent truncation, which means that we can rule out the stability of the 10D solution if this set turns out to be unstable. So what we can do is indeed look for a negative eigenvalue in the mass metric. And for example, if you work out the entry relative to the lower dimensional dilaton, you see that the right-hand side for the Sitter solution is negative for d bigger than 3, or whenever h7 is equal to 0 for d equal 3. So by subversive criterion, this is enough to rule out stability of the Sitter solution in this case, which again imply that, for example, the Sitter 4 is not, cannot be realized as a vacuum. And if you work out the eta v bound, this is agreeing with the refined. This is the Sitter conjecture. But one can now still hope for parametric control on the Sitter maxima or saddles. To address this point, one has to think about indeed this potential now has a tree-level part and a one-loop part. And therefore, we have to suppress the tree-level in order to compete with the one-loop term, but again, without generating a Dine-Seiberg problem. So ideally, we would like to have control on the solution by tuning unbounded fluxes, as they can help with the Dine-Seiberg problem. And this is also giving us another constraint, which is indeed the integrated Bianchi identity in the case of in the absence of local sources. So now, if I call RSS the average size of the Scherk-Schwarz torus and R the average length of the white space, and I define delta to be the ratio, I can write the full potential in terms of GS, the Scherk-Schwarz radius and delta. And here again, I would have the curvature, the H3, and the Ramon fluxes contribution and the Casimir. And from here, you would realize immediately that the two volume scales, so R and RSS, decoupled in the one loop term. So here, there's no delta, indeed, term arising. This means that we can suppress the tree level independently from the one loop term by taking R large, which means to we need to have a quite large anisotropicity in the internal space. However, we have to remember that the negative Casimir term must be leading because it has to break the strong energy condition. And now, if you compare it to the with the H3 flux contribution, we're going to see that this is indeed the condition. And this condition is compatible with coupling at large volume if and only if P3 is different than 0 and delta is much smaller than 1, which means again that the white space is sensitively bigger than the Scherk-Schwarz radius. So the internal space is anisotropic, and this is indeed the key to realize control. However, now if you remind yourself that the H3 0 component is the component that we need to have for the existence of the Sitter solutions, now we realize that this component must be leading with the Casimir, which means that we have to set trivially P3 equal to 0 here, so we are losing control by means of the absence of this delta, and therefore we understand here immediately that the Sitter solution is realizing the scaling that I told you, so GS has to grow with internal volume, and this constant is indeed a flux number, which is fixed to be an integer by rules of string theory. So here again, we are seeing indeed that the very same existent conditions for the Sitter are against the parametric control. But still, the question of numerical control is left open, even if it's hard. Control parametrically is not a problem for ADS solutions. So here I give you as an example a concrete solution, which is an ADS 7 times S2 times S1. So here we are breaking supersymmetry a la Scherk-Schwarz along this S1 direction. The solution is supported by harmonic fluxes. We have F2 threading the S2 and H3 the full internal space. And here you can work out the, so we solve all that in the equations, and you can work out the scalings for GS and then the two volumes. And here you can see that being the flux numbers unbounded, then we can crank up the flux numbers to reach the parametrically small weak coupling and large volume limits. So I will conclude with the following observations. We have explored type 2 Scherk-Schwarz orbifolds. They come with a negative one loop runaway potential that breaks the strong energy condition. And therefore, this is an interesting arena once embedded in flux compactifications where the runaway can be stabilized by fluxes and curvatures. I will then derive the Sitter theorems for instability and control. In particular, I show that there are not de Sitter for minima nor controlled saddles. On the contrary, ADS solutions under parametrical control are easily found. And here I conclude, so many thanks.
Many thanks, Marco. Any
right.
questions for Marco? Please unmute yourself and go ahead.
Hi, Marco. Very nice talk. You in none of your examples did you have a tachyon at threshold at the BF band threshold, or everything was safe?
For the ADS solutions, for the ADS solutions.
Yeah, for the ADS solutions.
So the solutions that I presented here is a ill solution in the sense that here the tachyon is indeed below the BF bound. So the main focus of the paper was on the control of the such solutions, and possibly on control on the Sitter saddles.
Okay, very good. Great, thank you.
Cheers, thank you.
Okay, any more questions for Marco? Okay, if not, maybe we can open questions for more speakers, but before, let me thank both speakers once again, so we can officially close the session now. And we leave the meeting open for remaining questions for both speakers. Thank you very much for attending, and we'll resume in 2 weeks on the 10th of December with talks by Luca Melotti and Nicolas Gatsos. Thank you very much. And I guess we can even stop the recording so people can ask questions more freely now.